Static load and theory of failures. Fluctuating stresses, fasteners bolted, riveted, welded, bearings sliding, rolling, friction devices, brakes, clutches, gears, spur, shafts, flywheels. Design. A process planned to satisfy the human need. Simplicity, creativity, design, iteration. Identification of need. Market survey, feedback, intuition. Specification, performance parameters, desired features, cost, life, etc. Concept generation, evaluation. Detailed design, prototypes, models, etc. Production, distribution. Machine. A machine is a combination of resistant bodies with successfully constrained relative motion used to convert other forms of energy into mechanical energy uh, or transmit and modify the available energy to do useful work. Machine design involves selection of suitable material and optimum dimensions to withstand the load without any failure. Load any external force acting on the member. Load static magnitude direction point of application constant with respect to time. Variable. Load time suddenly applied load 100 kilonewton like this. Load time gradually applied or static load it will be like this, which from 0 to 100 kilonewton gradually applied, then 100 kilonewton kept on applying. Variable load magnitude changes but direction remains constant. Example push rod, valve spring, railway carriage spring, helical compression spring, piston. Load magnitude changes but direction remains same. Camo, push rod, rocker arm, okay, cylinder, piston, connecting rod, ice engine, all are under variable load. All are everything is under variable load. Load magnitude constant, but direction changes. Example: railway axle. Magnitude is constant, but direction changes. Rotating shaft subjected to constant bending moment. Uh, a shaft is rotating machine element used to transmit power and support other power transmitting elements like gears, pulleys, etc. M P directly proportional to N into T. N is equal to constant, T constant, torque, coupler T1, T2. If we draw bending moment diagram, Mx here and then like this. Railway axle, sigma BT, sigma BC. This is bending tensile compressive. This is for railway axle. Point of application changes, moving loads, railway tracks, bridges. Stress sigma design stress sigma is equal to load by original cross sectional area is equal to F by AO. Sigma here F if E is equal to constant eccentricity, G is equal to G is centroidal axis E H L. F sigma 1 is equal to F by A plus M by I into Y. M is equal to F into E. Strain epsilon is equal to change in length by original length is equal to delta L by L. Hooke's law sigma directly proportional to epsilon within a proportional limit. Stiffness K is equal to load by deflection is equal to F by delta L is equal to F by FL by AE. Young's modulus K is equal to AE by L. Spindle a short rotating shaft. Short because stiffness is more. Motor spindle workpiece chuck. K is equal to EA by L. K increases, E increases or L decreases. These two not possible. L decreases short because stiffness is more. Stress at a point sigma is equal to limit delta A tends to 0, delta F by delta A is equal to dF by dA. Delta F is equal to delta Fx plus I cap plus delta Fij cap plus delta Fj k cap. X, Y, Z, F, dF, sigma ij I phase direction, J force direction. Here phase perpendicular to x axis, sigma xx is equal to limit delta a tends to 0 fx by delta a. Sigma xy is equal to limit delta a tends to 0 I by delta a. Sigma xz is equal to limit delta a tends to 0 fz by delta a. Stress at a point, stress tensor sigma is equal to sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. This is x phase, y phase, z phase. This is delta fx, delta fy, delta fz. These sigma x, sigma y, sigma xx, sigma yy, sigma zz tries to change volume, normal or direct stresses. These are all tries to distortion. Tau xy is equal to tau ix is tau yz is equal to tau zy, tau zx is equal to tau xz. Design for static load. Draw FBD. FBD. Sigma here tau xy, tau yx, these are complementary stresses. So this delta x into delta z into delta y into tau xy is equal to tau x into delta x into delta z into delta y. First forces, then a moment about corner, then moment about corner, delta xy is equal to delta yx. Principal planes and principal stresses, sigma is equal to sigma xx, tau xy, tau xz, tau yz, tau y, sigma yy, tau yz, tau zx, tau zy, sigma zz. These are all 0. Shears are 0. These sigma will be there. X plane, y plane, z plane. X plane, principal plane. The principal plane, a plane carrying 0 shear stress. Principal stress, the normal stress acting on a principal plane is called principal stress. Sigma is equal to sigma x. Principal planes, x plane, sigma principal stresses, sigma 1 is equal to sigma x, y plane sigma 2 is equal to 0, z plane sigma 3 is equal to 0. Biaxial stresses, sigma is equal to sigma x 0 0 sigma y. Thin cylindrical shell, sigma h is equal to pd by 2t is equal to sigma x, sigma l is equal to pd by 4t is equal to sigma y is equal to sigma y. Principal planes, principal planes, principal stresses, x plane, sigma 1 is equal to sigma x, y plane sigma 2 is equal to sigma y, z plane sigma 3 is equal to 0. Sigma l, sigma h, sigma h, okay, sigma x, sigma y, tau xy. The angle theta sigma x tau x, sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Tau theta is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. Here theta is taken anti-clockwise. So anti-clockwise, tau theta is downward. If upward, positive. Upward, negative half above formula. Tau theta is like this: sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. For principal plane, tau theta is equal to 0, tan 2 theta is equal to 2 tau xy by sigma x minus sigma y. Sigma 1 is equal to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy square. Sigma 2 is equal to sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 whole square plus tau xy square. Tau max is equal to root of sigma x minus sigma y by 2 whole square plus tau xy square is equal to sigma 1 minus sigma 2 by 2. These are can be solved by using above formulas. Tau max is equal to maximum of mod of sigma 1 minus sigma 2 by 2 comma mod of sigma 2 minus sigma 3 by 2 comma mod of sigma 3 minus sigma 1 by 2. More circle notation. Abscissa are normal stress, positive tension, negative compression, alternate shear stress. Sigma x, sigma y, tau xy, shear stress, normal stress. Sigma 1 comma 0, sigma 2 comma 0, tau max, tau max, Sigma x, sigma y, shear stress, normal stress. This clockwise positive, counterclockwise is taken as negative. Plane theta anti-clockwise, explain D plane. It will have sigma 1, sigma 2. Principal stress, blowhole start travels along principal plane. Explain perpendicular to x-axis. Simple tension, sigma, sigma, explain y plane, sigma comma 0, explain 0 comma 0. Sigma, this circle, assume this circle, 0 comma 0, sigma comma 0. Okay, x plane, y plane, 0 comma 0, sigma comma 0, 180 degrees apart. X plane, y plane, 90 degrees apart. So those two. Then draw a circle joining these two. Sigma by 2 comma sigma by 2 plus sigma by 2 comma minus sigma by 2. Sigma and this is G pen, this is F pen. Cup and cone failure or mild steel ductile material. For ductile material, they will fail by shear. So cup and cone failure, G plane, F plane. Cast iron brittle, what sigma, Y plane, D plane, Y plane, D plane, major principal plane. Principal stress sigma 1 is equal to sigma 2 is equal to 0. Maximum shear stress tau max is equal to sigma by 2. Torsion T or mx moment m bar is equal to mx I cap plus my j cap plus mz k cap. Here shaft is along x-axis. Mx is t by j is equal to tau by r is equal to g theta by l. T is equal to torsional moment. J is equal to polar moment of inertia of cross section is equal to ix is equal to iy plus iz. J is equal to pi by 32 d power 4. Tau is equal to shear stress at a distance r from center. G is equal to rigidity modulus. Theta is equal to angle of twist over length L. Torsion T or mx T by J is equal to tau by r is equal to g theta by L. Shear stress distribution tau by r is equal to T by J. Tau directly proportional to r if T by J is equal to constant. Tau min is equal to 0, tau max is equal to 16 T by pi d cube. 16 T by pi d cube. 1, 2, 3, 4. Carry maximum shear stress. First crack occurs on diameter. Tau x plane 0 comma minus tau y plane 0 comma tau. X just imagine x plane cut along x axis. It will have tau like this. It will have tau x plane or y plane. If we cut it will have shear stress like this. So 0 comma tau minus tau comma principal stresses sigma 1 is equal to plus 2, sigma 2 is equal to minus tau. Maximum shear stress tau max is equal to tau. X mild steel shaft to X plane, G plane, shear stress plane. This is tau max shear stress plane. So it will all shafts fail across diameter, breaks in least resistance path. This is a helicoidal failure or D plane. Cast iron plane, sigma 1 maximum plane. Pure shear sigma is equal to 0, tau 0. Sigma is equal to sigma 0, 0 minus sigma. Sigma 1 is equal to minus sigma 2, tau is equal to sigma. Bending moment m, bending equation m by I is equal to sigma b by y is equal to e by r. M is equal to bending moment, I is equal to moment of inertia of cross section about neutral axis. X, Y, Z, M, x. In this case, neutral axis is z axis. Sigma b by y is equal to m by I. Sigma b is equal to m by I into y. If m by I is equal to constant, sigma b directly proportional to y linear. Linear, it will be minus sigma b here plus sigma b here, compresses sigma b. Bending moment diagram should not show on cross section, should not be shown on cross section, and because it is not torsion, should be shown like this. On an interview, it may be asked. Bending moment problem, uniaxial shear stress biaxial, shear stress biaxial bending moment, either this plus sigma b plus sigma or minus sigma b minus sigma. Because if we take top, it will be like this. If we take bottom, it will be like this. Use either one of above two circles based on failure. Halo shaft torque, then it will be like this. Sigma b, it will be like this. Tau min is equal to tau max small d by capital D not equal to 0. Sigma b min is equal to 0 occurs at neutral axis. Sigma b the distance of d by 2 is equal to small d by capital D sigma max. Hydrostatic stress. Under hydrostatic pressure, they can carry more loads than usual. Sigma 1 is equal to sigma 2 is equal to sigma compressor tensile. Tau max is equal to sigma min minus sigma max by 2 is equal to 0. Thin spherical shell, sigma. Point on more circle, R is equal to 0. X sigma comma 0, Y sigma comma 0. Theories of failure. A component is said to be failed whenever it is unable to perform its designated function satisfactorily. Elastic failure, excessive elastic deformation, permanent deformation, fracture. To predict the load carrying capability of material under complex load, to predict suitable factor of safety. First theory, maximum normal stress theory or Rankine's theory. A component is subjected to complex stress is said to be failed when the maximum normal stress in the material exceeds the strength at the yield point under simple tension. If sigma 1 greater than sigma 2 greater than sigma 3, maximum then sigma 1 greater than or equal to SYT, then it is failed. To avoid failure, sigma 1 less than or equal to SYT or sigma 1 is equal to SYT by FS for ductile material. Sigma 1 is equal to SUT by FS for the brittle material. Ductile plastic deformation or distortion, SYT is equal to SYC. Brittle fracture or separation failure, SUT not equal to SUC, SUT less than SUC. Mild steel, the diagram will be like this: yield point, elastic point, plastic point, ultimate SUT, SYT. Cast iron brittle, it will SUT will be here. Rankine equation, sigma 1 is equal to SYT by Fs ductile, sigma 1 is equal to SUT by Fs brittle. Effects of Rankine theory. This theory gives good results for brittle materials, neglected the effect of other stresses, sigma 2 and sigma 3 in graph. Minus sigma 1 plus sigma 1. Fixed point is not always critical point. Put all loads, then decide. Rankine's graph square for ductile material. SYT, sigma 1, sigma 2, SYT, SYC, SYC, SYT. Brittle material, also it is square only, but here SYT, SYT line, SUC, SUC line. Total length SUT plus SUC square. Guest's theory or Tresca's theory or maximum shear stress theory. A component is subjected to complex stress is said to be failed when the maximum shear stress exceeds shear strength at yield point under simple tension. Exceeds shear strength at yield point under simple tension. Generally, shear stress estimated by torsion test. But here it is like this: tau max is equal to maximum of mod of sigma 1 minus sigma 3 by 2 mod of sigma 2 minus sigma 3 by 2 come mod of sigma 1 minus sigma 2 by 2. Shear stress. Shear strength at a point SSY is equal to SYT by 2. Tau max, 3 circles SY is equal to SYT by 2. If sigma 1 greater than sigma 2 greater than sigma 3 and all are alike, then tau max is equal to sigma max minus sigma min by 2 is equal to sigma 1 minus sigma 2 by 2. Sigma 1 minus sigma 3 by 2 is equal to SYT by 2 into Fs. Sigma 1 minus sigma 3 by 2 is equal to SYT by Fs. Validity: this theory is valid for ductile material. Most conservative theory flaw: neglected intermediate stresses. Graph sigma 2 is equal to SYT, sigma 1 SYT, then Tresca's hexagon. Guests most conservative, distortion most economical. Is conservative because it is completely inside all those things. Distortion most economical. Saint Venant's theory or maximum principal strain theory: a component is subjected to complex stress is said to be failed when maximum principal strain exceeds strain or yield point under simple tension. Epsilon 1 is equal to sigma 1 by E minus mu sigma 2 by E minus mu sigma 3 by E. Epsilon 2 is equal to sigma 2 by E minus mu sigma 3 by E minus mu sigma 1 by E. Epsilon 3 is equal to sigma 3 by E minus mu sigma 2 by E minus mu sigma 1 by E. Mu is equal to 0.5 rubber. Mu is equal to 0 cork. If sigma 1 greater than sigma 2 greater than sigma 3 and all are alike, then epsilon 1 greater than epsilon 2 greater than epsilon 3 and epsilon 1 is equal to maximum principal strain. Epsilon 1 greater than or equal to SYT by E fails. Design equation: epsilon 1 is equal to SYT by E into FOS. Sigma 1 minus mu sigma 2 minus mu sigma 3 by E is equal to SYT by E into FS. Sigma 1 minus mu sigma 2 minus mu sigma 3 is equal to SYT by Fs. Validity: not giving good results for either ductile material or brittle material. Graph rhombus: if sigma 1 sigma 2, if first quadrant, if sigma 1 greater than sigma 2 and sigma 3 equal to 0, then epsilon 1 is greater than epsilon 2. Epsilon 1 is equal to SYT by E. Sigma 1 minus mu sigma 2 by E is equal to SYT by E. Sigma 1 minus mu sigma 2 is equal to SYT. Higgs theory or maximum strain energy theory: a component is subjected to complex stress is said to be failed when maximum strain energy exceeds the strain energy at yield point under simple tension. Strain energy per unit volume for complex load UA is equal to half epsilon into sigma is equal to half sigma by into sigma is equal to sigma square by 2A. U total is equal to half sigma 1 epsilon 1 plus half sigma 2 epsilon 2 plus half sigma 3 epsilon 3. Replace epsilon 1 epsilon 2 epsilon 3 with these formulas of sigma 1 by E minus mu sigma 2 by E minus mu sigma 3 by E. Then after solving we will get 1 by 2E into sigma 1 square minus plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. U total greater than or equal to U yield point, it will fail. Design 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 less than or equal to SYT by Fs whole square into 1 by 2E. SYT by Fs is equal to root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. For 2D, sigma 3 is equal to 0. SYT by Fs is equal to root of sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2. Sigma 1 square minus sigma 2 square minus 2 mu sigma 1 sigma 2 is equal to SYT square. This will be ellipse, the rhombus inside ellipse. Validity gives an appropriate results for ductile material. Van Moises and Henke's or distortion energy theory or shear strain energy theory. U total is equal to U volume plus U distortion. Sigma 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 by 3 plus these. Okay, these three cases. Tau max volume change. Tau max is equal to 0. Hydrostatic. UD is equal to U total minus U volume. Sigma square by 2A minus of 1 minus 2 mu by 6A sigma square. UD is equal to 1 plus mu by 3 is sigma square. UD is equal to 1 plus mu by 3 into sigma 1 square plus sigma 2 square plus sigma 3 square minus of sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. Distortion at yield point UD YP is equal to 1 plus mu by 3 into SYT square. UD complex stress greater than or equal to UD yield point unsafe. 1 plus mu by 3 SYT by Fs square is equal to 1 plus mu by 3 into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. SYT by Fs is equal to root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. SYT by Fs is equal to root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 for 2D. Validity accurate for ductile material. It will be outside rhombus ellipse. Brittle maximum normal stress theory, ductile maximum shear stress theory, or maximum shear stress theory, or distortion energy theory. Safety maximum shear stress theory, safest is safe, size more less, cost more economical, factor of safety less more when loading is or when loadings are more. For maximum for Rankine theory, but not the safest. Fs is equal to SYT by sigma 1. If MSST, Fs is equal to SSY by tau max. Fs is equal to SY by sigma equivalent. Fs is equal to strength by working stress. For uniaxial, all theories predict same. Sigma 1 is equal to SYT. Design for fatigue. A component subjected to fluctuating load fails at a stress much below its static strength. This phenomena of failure is called fatigue. Crack initiation at point of high stress concentration. Crack propagation slow and progressive gradually. Fracture sudden fracture. Thin wire subjected to completely reversible load plus or minus m plus or minus m. Terminology mean stress or average stress sigma m is equal to sigma max plus sigma min by 2. Stress amplitude sigma is equal to sigma max minus sigma min by 2. Stress range r is equal to sigma max minus sigma min. Stress ratio sigma r is equal to sigma min by sigma max. Amplitude ratio is equal to sigma a by sigma m. These are all important because on previous gate question was there based on stress ratio or amplitude ratio. Fluctuating stress sigma max sigma min, it will be like this. Repeated stress, it will be like 0 sigma max 0 sigma max. Completely reversed load sigma max is equal to plus sigma min is equal to minus sigma. Here sigma m is this, sigma a is this. and repeated sigma r is equal to 0, sigma m is equal to sigma max by 2. Sigma r means stress ratio. Sigma r is equal to -1, here sigma is equal to m is equal to 0. Bending moment, bending moment diagram will be like this, shear force diagram will be like this, plus sigma minus 360 degrees. Waller 1870 IC engine, pressure experiences repeated stress, 0 to 180 suction, nothing will be the compression, repeated stress, again it will be like this, repeated stress will be there. Cycle before assembly preloaded by nut spoke design so that they will not fail by buckling. Compression tension W already compressed. Fatigue strength SF rotating beam rotating beam test motor coupling 7.5 mm dia R 250 mm specimen super finished removal hammer FX F1 F2 FN1 N2 so on. Coupling R is equal to 250 mm, here it will be there, Fx in Fx by 2 into L by 2. Sigma A is equal to sigma B is equal to 32 m by pi into 7.5 cube. Load applied completely reversal bending load. Sigma A SUT from SUT gradual decrease till 10 cube cycles, then steep decrease till 10 power 6 cycles, then constant then from 10 power 6 cycles. Low cycle fatigue 10 power 0 to 10 cube, high cycle fatigue 10 cube to so on. Here gradual decrease, here steep decrease for steel specimen. Here knee 0.5 SUT, this is 0.9 to 0.8 SUT. Low cycle fatigue, missiles, rockets, studs on wheels. High cycle fatigue, all bearings, engine, bolt, etc. 10 power 0 to 10 power 6 finite life, 10 from 10 power 6 infinite life. Endurance strength, life greater than or equal to 10 power 6 SC prime. It is maximum stress amplitude which a standard polished specimen can withstand for a minimum life of 1 million revolution under completely reversal load. Fatigue strength SF less than 10 power 6 mentioned with life. SF is equal to 100 megapascal, L is equal to 10 power 4, SF is equal to 150 megapascal, L is equal to 10 cube cycles. As it's with cycles, fatigue strength changes. Empirical relations, SC prime is equal to 0.5 SUT for steel if SUT less than or equal to 1400 MPa is equal to 700 MPa for steel if SUT greater than or equal to 1400 MPa. SC prime is equal to 0.4 SUT for cast iron. SC prime is equal to 0.3 SUT for non-ferrous metals. Endurance strength modifying factor, corrected endurance strength SC is equal to Ka, Kb and so on into SC prime. Ka, Kb are modifying factors. Surface finish factor Ka, SC is equal to Ka into SC prime. Ka, SUT 1.0 polished ground finished rolled forge, it will be like this. Size factor SC is equal to Kb into SC prime. Kb is equal to 1, D less than or equal to 8 mm. Kb is equal to 1.189, D power minus 0.097 or D greater than 8 mm. Reliable factor Kc, Sc is equal to Kc into Sc prime. Kc is equal to 1 for 50% reliability is equal to 0.897 for 90% reliability. Load factor SC is equal to Ke into SC prime. Ke is equal to 1 completely reversed bending, 0.8 axial load, 0.577 for torsional load. Stress concentration modifying factor Kd, SC is equal to Kd into SC prime. Kd is equal to 1 by Kf. Kf is equal to actual stress concentration factor is equal to 1 plus Q into Kt minus 1. St is equal to Kt is equal to Theoretical stress concentration factor Q is equal to Notch sensitivity factor. Stress concentration localized high stresses near discontinuity or stress sigma is equal to F by Bt. If there is a whole of D, nominal stress sigma T is equal to F by B minus D into T is equal to SUT by Fs. Theoretical KT is equal to maximum stress concentration factor. KT is equal to maximum stress near discontinuity by nominal stress. KT is equal to sigma max by sigma naught. Sigma max here, sigma naught here. Elliptical hole photoelasticity stress concentration sigma max is equal to sigma into 1 plus 2a by b. Here a is perpendicular to sigma infinite plate. If a is equal to 0, sigma max is equal to sigma. That means a line like this. If a is equal to b, circular hole kt is equal to 1 plus 2a by a is equal to 3. Kt is equal to 3. Sigma max is equal to 3 sigma. If infinite plate b greater than d, sigma naught is equal to sigma. If b is equal to 0, sigma max is equal to sigma into 1 plus 2a by b is equal to infinity. Non-destructive testing NDT. Effect of stress concentration on material static fluctuating. Ductile static no effect. KT no effect as it will merge. Fluctuating there will be effect. Ductile brittle there will be effect. KT static will be the effect and fluctuating also there will be effect. Ductile only and static loading as it will merge it will be and have less effect. SUT SYT is equal to 100 MPa, SUT is equal to 150 MPa, A is equal to 2b, sigma max is equal to 1 plus 2a by b into sigma is equal to 5 sigma. In ductile material under static load, the hole will deform and merge into the discontinuity. Under fluctuating loads, ductile material behave like brittle material. Notch sensitivity Q, the degree to which effect of stress concentration is actually reached. Q is equal to increase of stress actual stress over nominal stress by increase of theoretical stress over nominal stress. KT is equal to sigma max by sigma naught. Sigma max theoretical is equal to KT into sigma naught. Increase is equal to sigma max theoretical minus sigma naught is equal to sigma naught into KT minus 1. Actual stress concentration factor Kf is equal to sigma max actual by sigma naught. Q is equal to sigma naught into Kf minus 1 by sigma naught into Kt minus 1 is equal to Kf minus 1 by Kt minus 1. Kf is equal to 1 plus Q into Kt minus 1. Stress concentration factor Kd is equal to 1 by Kf. Corrected endurance strength SC is equal to Ka Kb into Kc into Kd so on into Sc prime. Effect of mean stress on endurance strength sigma max is equal to sigma m plus b, sigma min is equal to sigma m minus b. Sigma s, sigma m, sc, syt, sut, sigma m, syt, sut, sigma a, sc. This is Soderberg line syt. This is Goodman's line. Gerber's ellipse is this. Goodman's line y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. After solving, we will get sigma a by sc is equal to sigma m by sut plus 1 minus my sigma m by sut plus sigma a by sc is equal to 1. Sigma m by sut plus sigma a by sc is equal to 1 by fs. Soderberg's equation is sigma m by syt plus sigma a by sc is equal to 1. Gerber's equation sigma a by sc plus sigma m by syt whole square is equal to 1. Conservative theory for completely reversal load sigma m is equal to 0. So all will give same result. So all Infinite life L greater than or equal to 10 power 6 revolution. Goodman's equation sigma A by sigma E plus sigma M by SUT is equal to 1 by Fs. Economical Soderberg's equation sigma A by SE plus sigma M by SYT is equal to 1 by Fs. Safe. Gerber's line equation is sigma A by SE plus sigma M by SYT whole square is equal to 1 50% reliability. Biaxial stress, thin cylinder and shaft subjected to bending. Here it is taken on from base of 10. So use log, don't use ln. Better to use A is equal to SFL power B. A is equal to SFL power B. Design for failure, design for finite life. Sigma A 10 power 6, 10 cube, 10 power 8. Barkin's log S log n. Log S log n are straight lines. Barkin's equation A is equal to SFL power B. A and B are constant. B SF L is equal to 10 cube cycles. A is equal to SF 10 power 3B. C SC L is equal to 10 power 6. A is equal to SC 10 power 6B. B 3 comma log 0.8 SUT, C 6 comma log SC prime. We can solve like this. A and B are constants here. Cumulative fatigue minor equation, ball bearings, outer ring, ball, inner ring. Sigma n, n1, n2, n3 till that point this is applied, till n2 this is applied, so on. Automobile tapered roller bearing, inner wheels, let the component is subjected to only stress sigma 1, then its life will be L1. Life completed in one cycle is equal to 1 by L1. Life completed in N1 cycles is equal to N1 by L1. So on N1 by L1 plus N2 by L2, so on Nx by Lx is equal to 1. Divided by L, alpha 1 by L1 plus alpha 2 by L2, so on alpha x by Lx is equal to 1 by L. N1 is equal to alpha 1 L, alpha 1 is equal to percentage fraction of total life, L is equal to total life of our whole life, L1 plus L2, so on Lx is not equal to L. Modified Goodman's line, here sigma A SYT SUT static line load SYT SC SUT sigma A plus sigma M is equal to SYT by FS. SYT will be above sigma A by SC plus sigma M by SUT is equal to 1 by FS. Inside these both safe zone, intersection zone of sigma A by sigma M is equal to SYT by Fs, and sigma A by SC plus sigma M by SUT is equal to 1 by Fs. Modified Goodman's line, whichever is largest factor of safety is considered. Methods to improve fatigue strength. Two methods: mechanical working of metal, short pinning, hitting by balls, turbine blades, cold rolling, burnishing, hammering, coining, heat treatment, case hardening, gears, bearings.